We'll have the
Hello.
talk of Iván Panadero Muñoz from the Universidad Carlos III de Madrid.
Yes.
And the floor is yours.
Yeah, I'm also from Arquimea Research Center. So my name is Iván Panadero. You already know me. Also, hi from the online people. Yeah, I'm starting my PhD this year. I did my master thesis in quantum machine learning with Eric Torrontegui. He's from the Universidad Carlos III. And it was about yes, quantum machine learning. And now I'm going to start working with him in a collaboration with a company. So we're going to do especially the company is in Tenerife and he is in Madrid, Eric, and yes. Okay. No, no. Hola. Yes, perfect. So the work we're gonna do, I did was especially theoretical. We came from a theoretical background, but we are gonna switch to a more experimental and phenomenological experiments. So the idea is that we are going to use quantum machine learning techniques to set up a nitrogen vacancy lab. So especially for meteorological purposes, we are going to do experiments for measuring techniques. So we are going to talk here a lot about quantum metrology. So first we need to know what is classical metrology. First, metrology deals with what is a measurement. A measurement is just assigning a value to a physical quantity. We have done this in graduate experiments. So what we do is we can think about this value as a parameter, and each of these values has an uncertainty of how sure are we about of this value. The idea is that this uncertainty is something bad because we don't have a lot of knowledge about our system. So something we can do to reduce it is just repeat the experiment. So if we repeat the experiments a number n of times, this uncertainty narrows. So just as a Gaussian distribution due to the central limit theorem. So as we increase the number of repetition of the experiments, we have a narrower distribution. But this is in the classical sense. In the quantum world, as we are dealing with smaller phenomena, we can have other laws that govern this scaling in a sense. So quantum metrology with this deal, we need to take into account Heisenberg relationships and all these things. So now if instead of taking into account a number of measurements, we take into account a number of sensor and sub s, and we consider theta a parameter we want to estimate. The error we associated with theta scales as the number of sensor with the noise scaling, the one we are used to. But if the probes are entangled in the quantum world, as now the measurements we are performing are not entangled, they are not independent, so we have entanglement. And due to this not independence of the measurements between its sensors, we can get a Heisenberg scaling, which means that we have a squared performance, meta performance. So this is a quantum metrology in a sense, deals with these kind of things, but the good thing is now that we are capable of manipulating matter at the single atom level. So these quantum experiments have been here for a while. We can think about semiconductors or quantum interferometers that we already use, but now we can try to use the control of single spins and atoms to use these techniques and understand it. So we propose, so the idea is to use this to measure inhomogeneous fields. So the thing is that most of the times the system we use to measure are much smaller than the things we're interested in measuring, especially electromagnetic fields. We're usually interested in measuring the amplitude and the phase of those fields. But now sometimes if we want to measure something small, like a molecule or a protein or even a neuron, we want to study the charge distribution or the activation potential of a neuron. We need a protocol to study the inhomogeneities of those fields, especially inhomogeneities. So we propose this toy model. The idea is that we have a bunch of sensors, the red ones, and we want to measure the distance between two spin sources. The idea is that as we have this distance is a parameter we want to estimate, and as the sources move and they interact with the system, and through this interaction, we want to recover this distance. So R is going to be the parameter, and they will interact with a Hamiltonian that depends on the distance between the sensor and the source. In this case, it's important to notice that we are not considering entangling probes. Each of them are independent, because if not, the system will, the size of the system will increase exponentially due to the Hilbert space dimension, as we are already used to. So what we want to use is this Hamiltonian to evolve each of the sensors in this sense. And due to this evolution for a fixed time t, we get a spin distribution, so a mean value for the spin of the measurement. And from this mean value, we can recover the excitation probability that depends on this of this potential of interaction. In this case, we know it, but in other models, it might not be known. So from this probability, I don't know why it's not changing there. Sorry. Yeah, the thing is, I'm changing it here, but the thing there is stuck. It's connecting. This is trying to think. Yes. Sorry for the pause. So from this spin distribution, it's in the corner there. We have, like, for each distance, a probability of measure spin up or spin down for each of our sensors. So at the end, what we have is a collection of 1 or zeros for each of the probes that represents the probability that we had measurements. So for a fixed distance, we can repeat these measurements, because as it's a probability for just these sets of measurements, they can correspond to different values of R, and the other way around. For a set value of R, we can get the same values of 1s or zeros. So this is going to be our data, and that's what we're going to work with. And we can understand it as a collection of 1 or zeros, or we just can average and take the standard deviation of these numbers. So for example, in this figure, we plot this is mean spin value for each position of R for one single sensor. And in orange would be the mean value obtained from the measurements and the standard distribution. This corresponds to the error. So for example, if we increase the number of measurements, we would just have like a narrower error. So this is the image we should have for a set of more measurements for sensors in this case, but we can play with the number of sensors we are working with. So the idea is that we use a neural network to calibrate our system. So why do we want a neural network in the first place? So as I said, the interaction function that gives us this mean value is known in this case. So that's why we are able to generate the data. But in a real experiment, we might not know it, because the interaction can be more complex. So this is like the equation that relates, there's an equation that relates the spins we are measuring and the actual quantity we are interested in. So if we want to infer this error, we should do error propagation, but to know this function is not always the case, and it's not easy to get it. So even it can introduce nonlinearities and a lot of problems. So even you can do also some statistics to avoid this, but these are also another proposal we're having. So the idea is that we use the neural network to calibrate our system in the training procedure. So we use the value of R and a value of a distance we know. to generate these measurements of ones or zeros that we feed to the network. And we ask the network to output a value of R, this R hat. And with that, just do a regression training, and as we are used to. So this would be like the training as a calibration. And then we ask the network, the neural network to infer, to predict new values of R that hasn't been seen. And if this in the x-axis, we just have the index of these new values of R, and in the y-axis, we got in red the real value of R, and in blue the prediction we had. In this case, it was okay, but it was done with 4 sensors. But if we increase the number of measurements or increase the number of sensors, or even the time we evolve for system, we can have a better or lower precision. So especially for us, what is interested in is understanding how this precision, like the average of all of these measurements, increased as we increase the number of sensors. So we say we have again this is the scaling hat. So we compare with the soft noise scaling. That is the one we expected because each of the pros were independent. And what we found that is interesting, the same is that, or an important lesson, is that even if we fed the neural network with the ones or zeros or with the mean values, due to the fact that they both come from a binomial distribution, the performance of the network was the same, even if when there's ones or zeros, it has more data. But it's important that if we perform operation with the data, we have similar performance for the network. So this coefficient alpha will make this graph here in the x-axis is the log of the number of sensors, and in the y-axis we have the log of the error. So this coefficient just will move the graph up and down, but what we're interested is in the coefficient gamma that is the scaling. So other protocols would give different alpha, but if the probes are entangled, we should expect another change in this gamma coefficient. So other thing we were working on is we studied quantum neural networks, and we wanted to find out an application for them. So we wanted to study how they perform in this training data, in this data set. So the idea of a quantum neural network, as I've been already explained, in this case it's just for 1 qubit. So we have a ground state, we know, and we want to evolve to a target state. And we do it by applying to this state a set of gates that correspond to rotations, in this case an X and then an Y rotation. And the angles of the rotations depends on the parameters we want to minimize and in the input data. So at the end of this set of layers we apply, this is a set of rotations at the same, we evolve to a desired state, and we want that when we measure these states, we recover the value of R we are interested in, the distance. In this case, we did it first we studied for a simple regression task. So in this case, this sigmoid function, and we had 3 different, here we present 3 different layer networks, one with 2 qubits and introducing entangling gates in each of the layers, other with also 2 qubits, but without entanglement between the layers, and just 1 qubit gate. And we see that the 2 qubit was the best performer, but in this case, it might seem that the 1 qubit is not a good network, but depending on the regression test we try to work with, we can do it better or worse. But in this case, the thing we are interested in seeing that entanglement is usually a good resource for the network. So what we did is just use these quantum neural networks and use 2 sensors as to generate the input and work with the metrological task to recover R. So we see a similar graph, and this network was able to predict, in a sense, these values. But what we're interested is, again, now to focus on the network and which resources we have. So we did 2 kind of experiments. The first one was to fix the to increase the number of layers. So now we have more parameters at the same time, and in 2 senses. When these layers, this is for a 2 qubit neural network, when these layers had entanglement between each other, or where there was no entanglement between the layers. So when we see that when there's no entanglement, both for the prediction and training set, even though we increase the number of parameters, the quantum neural network is not able to perform any better. But even though we introduce entanglement in all the layers and more parameters at the same time, we see a change, and we see a better performance on the network. And at the same time, what we did next is we fixed the number of parameters of the layer, the number of rotations. But now, in this case, we only had 10 layers. But now we've increased the number of entangling layers we introduced in between those 10 rotations, these 10 layers. So randomly, for example, for one of these points, the network would have like just 5 entangling layers or 4 or 3. So the thing is that now the number of parameters is fixed, but the entanglement increases. So as we do this, we see that the network at least tries to perform differently in the training and prediction set, and has better results in this sense. This can be understood as when you introduce entanglement, your quantum state has more state that can access. The Hilbert space dimension is the same, but now you can access to more state to perform this processing of the data. And to conclude, just the important points I think is that entanglement is a good resource for a quantum neural network, and it's something is worth studying and stop it. In other cases, we could also have done it with a 3-qubit or 4-qubit neural network, but increasing the number of qubits also increases the possible ways you have to entangle your qubits. So we have this simple 2-qubit network and see the effect of entanglement. And then we could use this to reconstruct in homogeneous fields. That is an important metrological task. And finally, is using these ideas and combining with control strategies and quantum optimal control and other minimization techniques to use them in sensing with nitrogen vacancies. And that's it. Thank you for attention, and thank you also for my supervisors and everyone. Thank you.
So thank you. Are there some questions regarding these talks? So maybe I have one question.
Yes.
Because you were showing this, could you come back to a slide where we're discussing about the sigmoid and the 1-qubit?
Yeah.
So I mean, here, when you mean layers, could you show a bit more what you mean by the architecture that you're saying here? So
yes, here this L sub I consists of two rotations, one apply after the other. The thing is that at least you need 2 rotations because you want to cover your block sphere. So in this qubit sense, we applied then in this if this one just 1 qubit. So the number of rotations is the number of gates consists of these sets of rotations in itself. So the thing is that you have an X and Y rotation to apply, and then you will apply them again a number of times. So to increase the depth of the network in this sense.
Because I think if you do this kind of re-uploading scheme that Alba was discussing also the other day, I think this is a universal approximator. So I think already with 1 qubit, you should also be able to reproduce this kind of sigmoid.
Yes, you're able, but the thing with 1 qubit you can approximate, but depends on from like the goodness of the fit will also, for example, depend on the x-axis, like the interval you take the data, and this we are able to perform one qubit fit quite good, but it will depend on which range we are studying. This I don't know if it's clear.
Yes. Okay. Are there other questions? If not, let's thank Iván again.
Okay.